Hi friends, going through example 2. Now we're going to determine if this ordered triple is a solution to the system shown. This is a lot of tedious work because you have to check each one until you find where it doesn't work. So as soon as you find where it doesn't work, then you're good to stop there. However, I want to check each one to see each row is a solution. Remember, we substitute by plugging it in for the value. So this is going to be 1 plus 4 times negative 2 minus 3 equals negative 10. So check that one first. So I have 1 plus negative 8 minus 3 equals negative 10. So 1 plus negative 8 is negative 7. Negative 7 minus 3 equals negative 10. That does in fact equal negative 10, so that works. So the first one works. Now I'm going to check the second one. 2 times 1 plus 5 times negative 2 plus 8 times 3 equals 4. So that's 2 minus 10 plus 24 equals 4. 2 minus 10 is negative 8. Negative 8 plus 24 does not equal 4. What is that, 16? 16 does not equal 4, so that doesn't work. So this is not a solution. So now checking the bottom. So I have 3 times 1 plus 2 times negative 2 minus 3 equals negative 4. 3 minus 4 minus 3 equals negative 4. 3 minus 4 is negative 1. Negative 1 minus 3 is negative 4, so that does work. Check the second one. 2 times 1 minus 3 times negative 2 minus 2 times 3 equals 2. 2 times 1 is 2 plus 6 minus 6. 8 minus 6. 2 does in fact equal 2, so that one does work. And then now the last one here. So x1 minus negative 2 in parentheses plus 2 times 3 equals 9. So 1 plus 2 plus 6 equals 9. 1 plus 2 is 3. And then 9 does equal 9. So it is. Negative 2, 3 is a solution. That means this point is a solution to this system of 3 variable equations. So before we go in and solve, we're going to first jump in and talk about kind of the steps to solving. When you solve these, the steps to solving, we say that they're said to be equivalent if they have the same solution set. So both of these different systems here have the same solution set. These are equivalent. One of these is a lot nicer to work with. If you look at the second example, we can solve it easier because we already know what the third variable is, so we can back substitute this back into this one. That would then give us what this variable is. Then we could substitute both of those and then find out what x is. So we call this back substitution, where we find one of the variables, back substitute it, and do that. So what we want to do is basically use these different rules to be able to back substitute. So here I have this example. We can change the order of the equations. We can replace an equation by a non-zero constant multiple of that equation. So multiply the row by a number, or replace the equation with the sum of 2 equations from the system. So adding 2 equations, adding 2 rows, replace one of the 2 added rows. This produces an equivalent system. So we want to have an equivalent system, otherwise we're introducing whole new types of ideas which don't give us valuable, usable results. So this is our method for solving. We're going to write each equation in standard form. So all 3 of them we're going to write in standard form. Most often we're going to be using x, y, and z. So there's x, y, and z. Capital A, capital B, capital C, and capital D are your coefficients. So if the x term in any equation has a coefficient of 1, we want that row to be row 1, if possible. And then we're going to use the x term in row 1 to eliminate the x terms from row 2 and then row 3. So the original R1 with the new R2 and R3 form an equivalent system that contains a smaller subsystem of two equations and two variables. So then we're going to solve the system and keep the result as the new row 3. Then what we can do is back solve that one back to the other two to get our final answer. So what we end up with is something that looks like this when maybe we have an equation that started out like this. So our notation here, this says take -2 times row 1, add it to row 2, and then that will become our new row 2. So this is kind of the path that we're following. So when we see this notation, this describes the path. I like to see the path when we talk about how we're working through these because it helps to find the actual answers. Join me in the next video as we talk about the path to solving example 3.